Our next topic is closure and interior of a set in a topological space. Let X be a topological space and A be a subset of X. The interior of A, denoted by int of A, is then defined to be the union of all open sets in X which are contained inside of A. Now, two facts about the interior immediately follow from the definition. Namely, that the interior of A is open. It's an open set in X because it's a union of open sets, so it is open. And the other thing is that it's a subset of A because it's the union of all open sets which are subsets of A. So that's why the union is also a subset of A. Also, if A is itself open, then the interior of A is equal to A. How? Well, you already have this containment. Now, if A is also open, then A is an open set in X which is contained in itself. So, in this union, A is also one of the sets whose union you are taking. So, A in that sense is also a subset of this. So, that's how combining those two containments you get equality. The closure of A, on the other hand, which we denote by either CL of A or using this more common notation A bar, is defined to be the intersection of all the closed sets containing A. So this is the intersection of all closed sets in X. I did not mention in X here, that's understood, which all have A inside of them. Now, just like the interior of A, the closure of A also has these properties which follow immediately from the definition, because it is the intersection of a number of closed sets. So, the first thing is that it is itself closed, and then all those closed sets contain A inside of them. So, the intersection also contains A inside of it. Also, if A is closed, then A closure is equal to A. You already have this containment which is always true. Now you think of the reverse containment when A is closed. Just like this one, this is also very easy, so I leave that to you. To see how closures of subsets depend on the ambient space, we next have this theorem. Let X be a topological space where Y is a subspace. A subset actually which will become a subspace if you consider the subspace topology on it, and let A be a subset of Y. Now, A is a subset of Y as well as X. So, what will happen to the closure of A as a subset of Y and as a subset of X? These are not necessarily the same set, and actually they are not always the same set. This is how they are related. Then, the closure of A in the subspace Y is A bar intersection Y, where this A bar is the closure of A in X as a subset of X. So we start the proof like this. Let B be the closure of A in Y. If again go back to the definition of closure, this just means that B is the intersection of all closed sets in the subspace Y which contain A inside of them. Since A bar is closed in X, which we saw just now, in the definition itself, so that is why A bar intersection Y is closed in Y, and that comes from theorem 17.2, which gives us structure of closed sets in a subspace. Now you also have this. A is a subset of A bar intersection Y. How? Well, we already know that A is a subset of A bar, and in the statement of the theorem, it's given that A is a subset of Y. So that's why A is a subset of this intersection. Now, this is a closed set in Y which contains A, and B by definition is the intersection of all closed sets in Y which contain A. So, obviously B will be a subset of this. Also, B is closed in Y because B is the closure of A in Y, and closures are closed. So, that is why again by that theorem, B will be of this form. B will be equal to C intersection Y for some set C that is closed in X. Next, we concentrate on this containment. A is a subset of C. How? Well, what is A? And what is the relationship between A and B? B contains A because B is the closure of A in Y. So, after all, it contains A. So A is contained in B means A is contained in this intersection, but this intersection itself is contained in C, so that's how A is a subset of C. And because of this fact, A closure, the closure of A in the original space X is also a subset of C. Why? Well, what is C? C is a closed set in X and C contains A. So that means C is one of those sets whose intersection is this A closure. So the intersection would be contained in C, that's why. However, what does this imply? It implies that A bar intersection Y then is a subset of C intersection Y, which however is B. So that's how you have the reverse containment of this one. This one says that B is contained in A bar intersection Y, and this one says that A bar intersection Y is contained in B, and that's why they are equal. That means the closure of A in the subspace Y equals the closure of A in X intersection Y. So here the proof ends. Say you have a topological space in which you have a subset A. Now it's a bit difficult to find out the closure of A using the definition itself, because just like the topology of a space can be very large, there may be many open sets, there may be many closed sets also, and as you already know, closed sets are nothing but complements of open sets. So if you have a subset A, to find the closure from the definition, you have to know all the closed sets which contain A inside of them and then take their intersection, which becomes a daunting task if there are many such closed sets which contain A. So instead, we need something else that will help us to find the closure of some subset in a practical way. And that is why we have this next theorem. Let X comma tau be a topological space in which we have a subset A. Then a point X belongs to the closure of A if and only if, IFF means if and only if, for every open set U in tau in the topology which contains X, U intersects A. That means the intersection of U and A is non-empty. And there is a part B also. In part B, we assume that the topology tau is given by a basis, this script B. Then again, another such statement, this time X belongs to the closure of A if and only if for every basis element B which contains the point X, that basis element intersects A. The proof to part A starts with this. Let X be not in the closure of A. So actually the approach here we are taking is that then we will prove that this does not happen. And then to prove the converse, we will assume that this does not happen and then prove that then this happens, that X does not belong to A closure. That means we are proving that each statement not the statement but rather the negation of each statement implies the negation of the other statement. So that just means that the statements are equivalent, only proved slightly differently than a direct proof. Then X belongs to the complement of A bar. I should have written this first, but anyway, because X does not belong to A bar, so X belongs to the complement of A bar. The complement of A bar, however, is in the topology. That means it's open. Why? Because A bar is closed, that we already know. And something else is also true, namely that this complement does not intersect A. So we have found an open set in the topology which contains X but which does not intersect A. So is that not the negation of this condition? This condition says that every open set U in tau which contains X intersects A. But here this is an open set in tau which contains X but that does not intersect A. You do understand why this intersection is empty, right? Why? Well, that is because this does not intersect A bar first of all, because it is the complement of A bar and A is inside A bar. So obviously this will also not intersect A, that is why. So this means that in this part we have proved that the negation of this implies the negation of this. Conversely, let there be an open set U in tau which contains X but which does not intersect A. Now we need to show that X then does not belong to the closure of A. Then X difference U is closed in X because U is open in X, U comes from the topology. Additionally, A is contained in X difference U. Because U does not intersect A, that means every part of U lies outside of A. So automatically A is contained in that outside, which is this complement. And additionally, X does not belong to X difference U, obviously because X belongs to U. So what have we found now? We have found that we have a closed set which contains A, but X is not in that closed set. Now this closure by definition is the intersection of all closed sets in X which contain A inside of them. So this set would also appear in that intersection. Because our X fails to be an element of that set, so X cannot be inside the intersection. That means X does not belong to the closure. So this is the converse part. So that means part A has been proved. Now we prove part B. Because we have part A available to us now, we can prove part B directly, and we start like this. Let X belong to the closure of A. Then for any open set U in tau with X belonging to U, that means for any open set which contains X, that open set intersects A, and that is coming from part A. In particular, for any basis element B also this same thing will be true, that if X belongs to B, then B will intersect A. Why? Because basis elements are also open sets. So that means we have proved one half of part B. Now we have to prove the converse. Conversely, let any basis element B which contains X intersect A. Now we have to prove that this is also true in general for all open sets. So next we take an open set U which contains X. Now we have to prove that U then also intersects A. Now since B is a basis for our topology tau and U is an open set containing the point X, so by the definition of a basis generating a topology, we will have a basis element B which will contain that point and will itself be contained in U as a subset. So first of all we have this, that B intersects A. Why? Well, what is our hypothesis in this part? That if B is a basis element which contains X, then B will intersect A. Is our B like that? Yes. B is a basis element and B contains X. That is why B intersects A. Or in other words, there is a point which is common to both B and A. But B itself is sitting inside U, so that common point will be inside U as well. So that is why U also intersects A. So here the proof of part B ends and the proof itself ends. Now we devise a simple way of stating what this result says, the result that we proved just now. If U is an open set containing X, we say that U is a neighborhood of X. In short, we will write NBD. So X belongs to A closure if and only if every neighborhood of X intersects A. In this way we can remember it more easily. This is a schematic diagram of the situation. This is your set A inside some topological space. Now this point X is so close to A that no matter what neighborhood of X you choose, that always intersects A. If that happens and only when that happens, X will belong to the closure of A. So closure is that type of set. Let us next see one example where we consider this subset in the topological space R, this open closed interval 0, 1, and the closure of A in R is the closed interval 0, 1. Let's apply that theorem that we proved just now and see why this is so. Let us first note one thing. When we define the closure of a set, there we noted that the closure contains the set itself as a subset. So that means this set itself will be a part of the closure. Okay, it is a part of the closure. And we do see from this claim that there is one extra point in the closure 0, which is not present in the original set. How is 0 in A bar? By this result, 0 is in A bar because for every neighborhood of 0, there exists an intersection of that neighborhood with A. You can consider this neighborhood of 0, for example. No matter how small you choose this open set which contains 0, and that is why we are calling it a neighborhood of 0, there always is an intersection of that neighborhood and this interval, no matter how small you choose this neighborhood. And in fact, here you can observe that actually we have chosen a basis element for the topology on R. So we are actually using part B of that result here, and that is how 0 belongs to A bar. Why do we not have any point on this side or on this side also inside A bar? That is because, say you consider any point which is a negative real number, then no matter how close that is to this 0, 1, you can always find a basis element so small which contains that point which does not intersect this A. And so again, by that part B of that previous result, that point cannot belong to A bar. Similarly for points on this side, and that is why A bar is this closed interval. And do you also see why we cannot possibly apply the definition of closure? How many closed sets can you think of in R which contain this, this set? There are infinitely many such closed sets, and also who knows how many different types of closed sets are there. So that is why we cannot, in most cases, we cannot hope to apply the definition itself of closure to find the closure. We have to apply this theorem. Next, we considered this subset B, which is the set of all reciprocals of positive integers, also considered as a subset of R, and the closure of B in R is B union this singleton set consisting of 0. I want you to go through a similar argument to see why this is so. Similarly, we have another one. If C is this set, the singleton set 0 union the open interval 1, 2, then the closure of C is that singleton set union the closed interval 1, 2. And for this also you argue similarly. And we have a few others also. The closure of Q, that means the rational numbers in R, is the entire R. The closure of the set of positive integers is the set of positive integers itself. So we don't get any new point here. The closure of the set of positive real numbers is the set of non-negative real numbers. And finally, let's consider one more example where again we consider that same interval in R, but this time as a subspace Y in R. And inside of Y we consider this other subset, this open interval 0, 1/2. Then the closure of this subset in Y by that theorem is A closure intersection Y, where this is the closure of A in R, which if you go through a similar argument, like that one, will be equal to this closed interval 0, 1/2. So you take its intersection with this open closed interval, you get this other open closed interval. So this is the closure of A as a subset of Y. And let's just end the video here. In the next topology video, we are going to see the notion of limit points.